Hey, this is another video from Mr. Mitchell. Today's video is about stars. Like our sun, all stars are huge balls of glowing gas that produce or have produced energy by fusion. Now, you may remember what fusion is. Fusion is when you take two molecules of hydrogen gas and it's so hot that it blends into one molecule of helium gas. And if you don't have fusion, you don't have the intense heat that you can get from the sun or from stars. And that's just kind of an essential. All of these stars that are in the distance here, you have to have fusion going on in their core just for us to be able to see them in the night sky, unless they're a reflection of something like they are off a moon or a planet. A few thousand stars can be seen in the night sky without a telescope. Now, these stars, of course, look very small to us because of their great distance from us. They actually are very, very, very large. To describe extreme distances like this, let me take a look at this little star right here. And sure enough, I'm using the wrong color. But take a look at this little star right here. And there's no telling how big that really is. But to us, it's just a little bitty speck. So you have to know that it's an incredible distance away. To describe extreme distances like you find in space, astronomers use a unit called a light year. Now, light travels just like sound travels. Sound travels at a much slower speed. Sound is something like 700 or 800 miles per hour. But light travels 186,000 miles per second. And you don't have to write that down just yet. But 186,000 miles per second means that light is going to, 186,000 miles is larger than the Earth. The light's going to be there just boom, boom past the Earth. It's the fastest thing we know of. So a light year is how far light travels in 1 year. If it's 1 second, it's 186,000 miles. So multiply that out toward a year, and a light year is the distance of 6 trillion miles. So light travels in a year 6 trillion miles. The closest of these stars to us is 4 light years away. So the closest of all the stars that are to us, it's 4 times 6 trillion, that's 24 trillion miles away. Wow, that's just hard to even comprehend. Some stars, as you can see, are brighter than others. Now, it may depend on how close they are. Here's a bright star right here. Here's a bright star right here, not as bright as the other, but this may be a planet here. But anyway, it may depend on how close it is, or it may just be a bright star. And we don't really know it just by looking up into the mist here, which is which, unless we happen to know that star. But here's how astronomers think they can figure out the distance of a star just by staying here on Earth. They use something called parallax. Something called parallax. Now, parallax, well, we kind of know the idea behind a parallax. That's the apparent shift in position of an object depending on where it's observed. For example, if you're looking at something like a clock and you hold your thumb up over the clock to where you hold one eye open and the thumb appears to cover the clock, and you hold the other eye open and it appears to move, your eyes have a different perspective because they have a different angle. So how do you do that with stars? Well, you do this. Oh goodness, you can't see this very well. But anyway, you can oh wow, that's good. Now you can see it well. But what you have here, you have the Earth. Now in January, or whatever set month, the Earth is this far from the sun. But then 6 months later in July, it's on the other side of the sun. We know that the Earth is going to travel X number of miles just by its revolution around the sun. So if astronomers check to see where the star is in comparison to other stars in, say, January, then 6 months later, see where the star is in comparison to other stars in July, then they think they can kind of see how far it is. For example, if this star were really, really close, if this star were much closer, then the vantage point would be much different. The stars you see behind it would be not the same stars you would see right here. Whereas if this star were very, very far away, let's go with a different color here. If this star were very, very far away, then you'd have another completely different things that would be behind it. So they're using the whole principle of parallax just to try to calculate how far the star is out, and they think they can come to within reasonable accuracy just by knowing where we are in our own particular solar system. Now let's go to this next slide right here. Some stars are larger than others, and some of them can be even 100 times larger than the sun. That's pretty large right there. There's actually a supergiant called Betelgeuse. That doesn't look like this would spell Betelgeuse, but there's a supergiant called spelled Betelgeuse like this that is actually 600 times larger than our sun. It's a superstar. Some stars are smaller than our sun, and stars called white dwarfs, there's white dwarf, spelled a lot easier, are about 100 times smaller in diameter than the sun is. And a white dwarf is roughly the size of the Earth. So down here you have a scale that is more in scale with the numbers than it is the size, because the white dwarf would be much, much smaller. If Betelgeuse were 22 miles to scale, white dwarf star would only be 1 foot. And our sun would be 38 yards, kind of in between, but still nowhere near what Betelgeuse is. Now you also see a couple of the terms here. A black hole would be much bigger than our sun. And a neutron star is going to be much bigger than our sun. And I think we actually cover these later on in this video or another one. So I'm going to hold off on a whole lot of explanation right here. Ooh, here's a relationship between our sun and a white dwarf planet. A white dwarf planet is way, way smaller. Some stars appear white. In fact, most of them appear white. But you may notice that a few of them seem to be slightly different in color, like, say, blue or red. Now, these approximations right here are exaggerated. You don't look up in the sky and see something completely red or completely blue like this. They are slightly that color. But scientists can think they have figured out a couple of things from this color. You can see that the surface temperature is higher for those that are blue than they are for those that are red. They think that they kind of have figured out what the temperature would be, because is different because of what color tint it looks like. Our sun is yellow, which is in between, of course. And scientists believe also they can figure out what gases burn up here because of this. You'll find out that the red kind of seem to burn up helium instead of burning up hydrogen like you have in the sun. So that's one indicator they think they have figured out from here. Stars form. How do stars form? Well, they form from a cloud of gas and dust, like here, called a nebula. So stars form from nebulas. Nebulas should look like this. And when you have all this material out in space close to each other, what tends to happen is they tend to pull itself together. And you know they're spinning around stuff. Even our sun is spinning around stuff. So as a result, they are spinning and they kind of tend to form together. And you can kind of see how this is over here. You have a nebula over here, and in this depiction, it looks like it's kind of creating a massive core in there. So as a result, I'll kind of skip forward. It will end up like a sun after X number of years. Oh, let me check back in my notes, see where I am. The sphere becomes a star if the center grows hot and dense for enough for fusion to occur. If you have things that are forming in space from a nebula, it's just not going to be a star without fusion. It has to have fusion to be able to be a star in the first place. Stars exist for a long, long, long time, but they are not permanent. Before stars die, they have here are the phases of their life. Now there are going to be two different tracks here. You have phases of a regular star, and you have phases of a massive star. Now our sun is going to be like one of these regular stars right here. These regular stars are going to be called lower mass stars. Lower mass stars like our sun can fuse hydrogen and helium for billions of years, astronomers think. I don't know about how they can determine that, but they think they're using the term billions of years in this. When it runs out of hydrogen, you know, hydrogen's essential for fusion. When it runs out of hydrogen, it expands. And when it expands, it's called a giant star. And in giant stars, that's when helium fuses into carbon. That's why I was saying some of these redder stars, they fuse helium, whereas our sun, for example, would fuse hydrogen. Checking out my notes here. Over time, the giant star sheds its outer layers. And we're not necessarily learning this term, but it sheds its outer layers. And as a result, it's going to become a small white star. Now, our book does not use the term black dwarf, but what happens whenever it comes to a white star, it remains hot, but no fusion occurs. You can see I have up here, we have the main sequence. I forgot to mention that. The main sequence is whenever it's fusing hydrogen into helium, then it's helium into carbon for a dying star, then it sheds its layers, and you have no fusion when it's a white dwarf. And it is more of a dead core than it is a star. Higher mass stars have a shorter main sequence because they're bigger and they're going to use up hydrogen rapidly. When these expand after they run out of hydrogen, they become these supergiant stars. An iron core forms and eventually fusion stops. So gravity causes the core to collapse. It erupts into an explosion. These supergiant stars, once they collapse, erupt into an explosion called a supernova. A supernova is very bright and propels hard materials out into space. Propels these hard materials out into space. Now, a collapsed core of a supergiant may form an extreme dense body called a neutron star. This is incredibly dense. They are only about 12 miles in diameter, but they're heavier than the sun. They emit a lot of waves like X-rays and radio waves. Pulsars like this don't seem to pulse with the waves as they spin. So a pulsar are these neutron stars that emit these waves. Sometimes one of these cores are so dense that it doesn't end up a neutron star. Instead, it collapses and forms a black hole. The gravity of a black hole is phenomenal. Last thing, sometimes two or more stars orbit each other. This is called a star system. To us, when we look up at them, they're too close together to be seen separately, We detect these when light is inconsistent over time and one star interrupts the light.